Yeah.
Right. So, yeah, hello everyone. So today I want to talk a little bit about the prediction of solid solution strengthening of alloys with Green's function-based DFT methods. So, as I said, this work mainly contains things that I did before coming here. So it's a little more elaborated, and the corresponding paper is near the submission stage. So let me start by giving you actually an overview about my today's talk. So firstly, I want to show you why high entropy alloys are especially interesting for us and how in particular we can model and predict the strength of such alloys. After that, I will give a brief comparison between the Green's function methodology that I was using there and that I basically learned here. And then I will show you the nuts and bolts of my workflow that I was using for predicting the strength and also do some detailed comparison to experiment. And lastly, I want to show you how all of this can be used for alloy design if combined with machine learning. So, yeah, so disordered alloys with multiple principal components, I think they're more commonly known as high entropy alloys, have attracted a lot of interest because of their favorable mechanical properties. So for most engineering applications, it's crucial that our material is not only strong, but also tough. So it basically means it can withstand a significant amount of plastic deformation before their catastrophic failure. And these single-phase solid solutions have actually a potential to overcome this usually strength-ductility trait of that one experiences in steels. And the reason for this is the reason for these favorable properties are on the one hand that they're mostly closed-back cubic structures with a lot of slip planes, and on the other hand, they have a very strong strengthening effect due to the many components in this solid solution. And the strong strengthening effects mainly come from the interaction of the dislocation here with the geometric lattice distortion that are introduced by the solutes, and also the locally different bonding environments that are created by the solutes. And all of this interaction increase the stress that is needed for moving the dislocation and deforming the crystal plastically. And usually we call this effect solid solution strengthening. However, it is clear that explicit calculation of this shear stress that is needed for deforming the crystal and moving the dislocation is effectively out of reach for ab initio methods. And so, but one can really reduce this complexity of the problem by using a model approach. So actually, this is the most coolest approximation I think that one can do. But so in this approach, the strength, so basically this shear stress that is needing for moving the dislocation along a plane and deforming the crystal is just giving as a function of some measurable or calculatable material properties such as linear elastic constants, equilibrium, volume, stacking force energies. In particular, I was using an experimentally validated analytical model for the strength, which was proposed by Barren and Curtin a couple of years ago, and which seemed to be quite successful according to the number of publications, the number of citations. And however, even calculating these properties for these these alloys with these multiple components that might even be paramagnetic is very, very computational demanding. And that's why, and this is actually our Green's function method offer here a great way to treat disordered systems with really reduced computational effort. And however, we also need to make in order to make our model predictive, we really need to accurately predict the elastic properties, or the linear elastic properties, and also these equilibrium volumes as accurate as possible. And that's why I somehow set up a quite elaborate workflow that will produce all of these results. So here you can see an overview of the workflow. So the input is just alloy with a certain compositions of its component. And my alloy calculator is a Green's function give T method where we employ some semi-empirical corrections to the exchange correlation function. We also include finite temperature effect. And we also use a supercell Green's function calculations to improve some parameters for the CPA. And yeah, this is mostly done really to ensure an accurate prediction of the equilibrium volumes.
Can you just mention very briefly what is the finite temperature correction that you introduced?
I will talk about that. So it's just an overview. So
Okay. It's fine.
And yeah, this calculator is then used for getting the linear elastic properties. And actually, also this quantity, which is used for the strengthening model, it's the dependency of the equilibrium volume on the variation of the concentration components. And the target quantity that we get from our workflow is this critical resolved shear stress. Okay, so we in our group use a slightly different methodology than LSMS to perform our alloy calculations. And this is the so-called locally self-consistent Green's function in LSGF, which basically serves the same purpose as LSMS, and which was developed by Abrikosov mainly like about more than 20 years ago. So instead of just calculating this finite sized local interaction zones or cluster around each size to get our respective tau matrix, we embed our clusters into a CPA medium. So we get really our tau matrices by solving the Dyson equation, where we have the T matrix, so the stock diagonal T matrices from our clusters, and these transformed T matrices from our CPA. We always do one CPA step and run a real space cluster step in each SCF iteration. The main advantage of this whole thing is that you just need way smaller local interaction zones to get converged results as compared to LSMS. And this is, I mean, very important because, of course, this makes the matrix inversion for the path operator a lot smaller. And yeah, so the reason why we're doing this in the first place, so why are we doing supercell calculations, I mean, is because we're including also these Coulomb screening effects into CPA. So I think I won't talk about that now, not in detail, because there were some presentations about it already. I just wanted to point out one thing here. So there is also one difference. So we not only include the monopole interaction when we calculate the Madelung potential, but also we include the monopole-multipole interactions. And for example, in this nickel platinum alloy, so there are some charge transfers already. It really makes a difference for the screening parameters when we fit the local Madelung potential to our monopole charge transfers. If we just take into account the monopoles, or if you also take into account the multiples for that.
But my question is, yeah, I mean, I could believe that the dipoles also play a role, but how come such higher, like you have 6, such high multiple moments are important? I mean, or is there are there numbers?
It's actually not. So it's really the monopoles and the dipoles are like are the most important here. Okay. It's just if you want to do surface calculations, then these things really start to matter. Also, if you want to calculate properties of how do you call it, of vacancies, then you also need to include higher order. But okay, 6 was a bad example. I should have shown everything, but yeah, mostly dipoles.
Okay, I see. Okay, nice.
Yeah. Okay. Yeah. Right. And the next thing is, I mean, okay, generally, even if we solve our equation as accurate as possible and treat everything as good as possible, there is still this systematic error in predicting the equilibrium volume that just comes from the exchange correlation function. So, but on the other hand, if you calculate these linear response properties that we need, like these linear response properties, like the linear elastic constant, they're reproduced quite accurately by DFT calculations if performed at experimental volume. So what we are now doing is we are taking all of these non-local exchange correlations effect into account in our LDA calculations by just adding a concentration-weighted component-specific pressure, as was proposed by Van der Waal. He proposed it actually for ordered alloys, but so we just extended this whole thing to our disordered alloys. Yeah. And this component-specific pressure is just calculated once and for all, basically for the ground state of each element. Okay, this can be also difficult. For example, for manganese, you have this large unit cell, for example, with this difficult magnetic state. But once this is done, it can be used for all of the alloy calculations. And as you can see here, by applying this pressure correction, one really improves the prediction of the equilibrium volumes as compared to, for example, GGA-BV. I mean, if you would take pure LDA, it would be totally off, of course. And this works not only for our iron group elements here, but it also works for these always containing these 5D elements. And this effect is even more pronounced for the bulk modulus, where our method only slightly underestimates the bulk modulus as compared to these GGA-BV calculations. And the good thing, it's a transferable methodology too. So, yeah, I also just wanted to note, because I haven't really seen it before in presentations, that CPA can also be used as a way to model the paramagnetic state above the magnetic transition temperature. So effectively above the magnetic transition temperature, the magnetic moments are starting to be non-collinear, they're fluctuating, and they effectively don't have any long-range order anymore. And ideally, even the short-range order disappears. So this is then considered as the ideal paramagnetic state, where you also don't have any short-range order. So it's now possible to model this state by CPA by assuming a pseudo alloy of equal amounts of atoms with spin-up and spin-down orientation in the local magnetic moments. And this is the so-called disordered local moment picture. However, generally these spins. Yeah.
Yeah, that's what Hubbard did in the Hubbard 3, or early on, I guess, for the pure Hubbard model. They managed to get a multi-insulator in this way. So that's consistent. That I just confirmed that this is in some regimes this works well.
Right. Yeah. Right. So this really helps with treating actually these transversal spin fluctuations.
Right. I just want to mention, you may ask, for the Hubbard model where you don't have any complexity or real structure, but you can ask this question: when is this approximation correct? And my understanding is that in the multi-insulator, far enough from the transition, that's perfectly fine. You can get a Hubbard bands and everything from this. Where it doesn't work very well is in the region where you can start forming quasi-particles, because that's where, this approximation assumes that the local moment is fixed. And on the metallic side, you can form a Fermi liquid by conduction electron flipping the spin coherently back and forth. That's a Kondo-like processes which cannot be done in this static way. So there is a region, but that region is not particularly large. I think that's where you, for example, need the MFT. But probably for most of the phase diagram on the insulating side, you don't need anything better than this CPA. So I would agree with you. This is probably for many cases actually all they need.
And I'm also not so sure if actually, we're talking about room temperature or slightly elevated temperatures are already quite high temperatures. I think that also helps with all of these things. So
right. Well, my point is that, if you take just the Hubbard model, you can do exactly the same thing, and they've done it. Hubbard has done this, and so you can now benchmark this against more accurate theories like CPA, like DMFT, but the disagreement with that is limited to some range near the transition, which is perhaps not too broad, the critical range. So I'm saying that, in the old days, this looked like an ad hoc theory, but now it can be benchmarked. And in fact, I think that's something interesting that has never been done and published, actually, I think in great detail, but I think it will be interesting to ask, when does this break down? When does it work, for more simple model Hamiltonians?
And I just wanted to also mention one more thing here. So generally, the spins are not actually only rotating, but they're also fluctuating in its magnitude. And so at elevated temperatures, especially for I think itinerant systems, this can really enhance the local magnetic moment. And of course, we cannot include these longitudinal spin fluctuations really on a quantum level in this single body theory, but we include it with a phenomenological function. Now let's get back to, so I ignored now the temperature effects. I did not make a slide for the phononic effects. I mean, electronic is clear. We just use a circular contour there, and the magnetic effects are included by our LSGF. So by our longitudinal spin fluctuations and the magnetic entropy, and the phononic effects are included after the calculations by a really simple Debye-Gruneisen model.
I see. Oh, but by the way, concerning the magnetic moment length, that's what you mentioned here. I think one can say, I mean, I'm just saying from I'm a DMFT guy, from DMFT perspective, it's the Kondo processes which reduce the size of the magnetic moment and can destroy it by on the metallic side by forming the Fermi liquid. So I'm just saying that, if you compare this theory and DMFT, you can see where it doesn't work. And part of this is, in fact, that I think DMFT can include these longitudinal spin fluctuations, if that's what you want, the language you want to use. In the DMFT community, they don't use this language. So that's why I'm mentioning, because it can be confusing. Is this something completely unrelated or cannot be connected to DMFT? I think no. I think there is, part of what you're talking is actually included in DMFT, but not in the entire phase diagram.
Right, yeah. So actually, it would be cool if there would be some like combined study that brings these languages together, because there are some groups which are using these phenomenological functionals quite successfully, but I haven't really seen detail. I mean, I also don't know if that's really that possible.
I would like to do that very much, because, for example, they talk about bad metal behavior in some system, linear resistivity at high temperature. I haven't actually done this yet, but I think that this approximation will give you that. So there are lots of regimes where something strange happens, which I think can be captured. And I think if you want to build a computational suite for materials, you really need this simplification and know where it's reliable. And I think it's more reliable than what some people from the field theory background think. Anyway, sorry.
Yeah. I'm asking these questions myself too, because it's a phenomenological functional with a lot of parameters that are just more or less given by God, more or less, something like that. And it's hard to really, justify that. As mentioned earlier, the dislocation motion is really impeded by these elastic fields of the lattice distortion which is introduced by the solutes. And one way how to quantify this lattice distortion can be done by this quantity. It's called it's the volume misfit between the solute and the matrix. In short, we call it misfit volumes. And this can be calculated by considering the dependency of the equilibrium volume on the variation of each component's concentration in an atom. And the easiest way how to actually calculate that is to always fix the ratio between the rest of the elements, and just change one component here. And okay, this is now over a really large range. But what you can see here is that you just take very small region here that it's mostly linear, the concentration dependency of equilibrium volume. And this also helps then in the future if you really want to quantify that with experimental results. So in the near region, this really works well. And of course, it's very easy for us to calculate this property.
So by the way, you say linear, and I understand that it must be linear over some finite range, but my guess would be that if the concentration of one species is very small, then it should also be linear, but maybe the slope is different. Are there data testing this when this percentage is very, very small?
So yeah, that's true. So, and for example, I think so one particular example is PCC iron chromium, because there you not only have, of course, then there are short-range order effects come into place too. So one really cannot just do CPA, but one has to do like LSGF or LSMS. And if one does the same thing, okay, it's the super heavy calculation, but the slope will be the difference. So it will be, so if one does the same thing in iron chromium PCC for chromium, one really sees a slope here. It's not just linear. Yeah. And here, I just took this very simple nickel cobalt chromium example. And the reason why I took this is because this is a very rare example where direct measurements actually exist. So where really people varied the concentration, the concentrational content of the elements, and did this experimentally, and really also tried to control the parameters of the experiment. And in this study, they also tried to predict the equilibrium volume and these so-called misfit volumes with different theoretical methods, I mean DFT, but also with supercell methods and also with the Green's function methods. And they failed basically in both cases here. So this is one study actually. And compared to this, so our full model can really reproduce not only the equilibrium volume, but also the misfit volumes quite accurately. I mean, you see here some discrepancy, but effectively, if one puts here an error bar, which is introduced by this error in the measurements, I mean, mostly in the error of the concentrations, then it fits pretty well, actually. And as shown before, we can predict the misfit volumes and the equilibrium volumes with our workflow. Now, with what we are aiming at is the prediction of the temperature dependence of this critical resolved shear stress, so the stress that is needed for moving the dislocation, and compare it to experimental results. And this solid solution strengthening contribution has two main sources of temperature dependence. So one is an kind of Arrhenius-like dependency just due to thermally assisted crossing of the energy barriers of the dislocation. So this can be, this will be really just an Arrhenius-like dependency of this quantity with some energy prefactor that can be calculated in the exponent. And the other thing is also the linear elastic constants and the misfit volumes itself are temperature dependent. So the misfit volumes, I mean, even though you have thermal expansion, the misfit volume is actually quite constant here. But you really have a significant softening in the linear elastic properties. And if you combine this to the model, you'll see that our workflow can actually really predict quite accurately the experimental value for this critical resolved shear stress. But for example, if we just take the material parameters for 0K and not calculate it for each temperature point, we get a slightly different behavior here. So it's really important, even though the energy barrier is only very weakly dependent on the temperature, it has a quite significant impact. So you can see that on this left middle. Okay, and after this, I now then embedded this workflow into an optimization loop. Since this workflow is quite computationally expensive, we need a really efficient sequential update strategies to get the global maximum of our critical resolved shear stress in a minimum amount of steps. And in particular, this Bayesian optimization can give us this global maximum with about 15 to 25 steps. But maybe one has to go now one step back. So actually, in this plot, you can see this critical resolved shear stress, so actually the strength, as a function of the concentration of one component, while the ratio amongst the others are kept constant. So what you can see is that our target quantity here is the critical resolved shear stress is actually a quite smooth quantity. And this also really helps in finding the maximum really fast. And this also really shows that it actually makes sense to do this optimization in this certain range. But of course, you see, even though these are already 32 points, and I haven't really screened through all of the concentration of combinations here. So, and if I do the same thing with the Bayesian optimization, it will give me a maximum, a global maximum in 20 steps. So it's really fast. And now I want to show you how this Bayesian optimization works. And again, on a simple example, effectively two-dimensional simplex here. And there are always two quantities involved in finding the next point in this for the optimization. So the starting points are basically my corner points here, which I know, 0, the strength here, and just 3 random points chosen somewhere in this simplex. And so the first important quantity is the interpolation between all of these points. And this interpolation predicts the maximum of my function. And the next thing is the connected uncertainty of my prediction. So of course, around points where I sample the simplex here, this concentration space, a lot, the uncertainty is low. And both quantities together will then determine the next point. So finding the next point is always a balance between the exploration of regions with high uncertainty and exploitation of regions where the maximum is supposed to be already. So somehow the next point will be in this region. Of course it is. And here you can see I just made a small kind of movie about how this optimization process is finding the maximum. For example, here you have the high uncertainty in this region. That's why it tries to also sample this. Right. And now I do a very sharp turn. So all of the work that you saw before was done before coming here. And now it's really something that was mainly done here. And it's just a very short introduction actually to that. So as I mentioned before, there are different ways on how to model the paramagnetic state. So really some of the brute force way, and maybe in some cases also the most accurate way, would be to just have a large supercell and distribute our magnetic moments in a way that they fulfill certain conditions for the correlation functional. And of course, we can also use the disordered local moment picture with CPA. And a few years ago, Professor Ruban proposed the so-called spin wave method, which is actually also in a way very similar to the supercell approach. So it's more or less a subclass of that, I would say. So the basic elements of the spin wave methods are these planar spin waves. And the correlation function of these planar spin waves are given here. So it can be now really shown that equally weighted superposition of all of the possible spin waves that one can set up for a certain lattice yield to an ideal paramagnetic state, meaning a paramagnetic state where the correlation functions are vanishing. So one doesn't have any short-range order here. However, it's now by no means clear on how this will help us model the total energy with this finding here. However, since our systems are really Heisenberg systems, also the same integral over the total energy over all of these states will give us the energy of this ideal paramagnetic state. But since we do actually not have to, of course, calculate all vectors in our Brillouin zone, we can just reduce this integral to a sum of these individual total energy points of a set of these spin waves or spin spirals in the irreducible part of the Brillouin zone. And they are then just weighted according to the symmetries. And this is not just like convergence tests for BCC iron and for FCC cobalt. So what you can see here, it's always a comparison between non-magnetic, ferromagnetic, and DLM where it was possible. And for sampling the Brillouin zone, I did effectively, I used effectively 3 different methods. So the first one is just the mean value point, the Baldareschi point. And the second one, I took the Chadi-Cohen, the 2 Chadi-Cohen points for BCC and FCC. And in the third case, I really took a Monco-Spack scheme to get the corresponding K vectors. So, of course, in real space, in reciprocal space methods in EMTO, one can do DLM, but one can also really set up these non-lattice periodic spin spirals. In LSMS, one cannot really do that because the only way how one could set that up is like by really by some real space spin waves that are then periodic. So one really has to, if one does, so how I was doing that in LSMS is just I was using non-collinear magnetic moments. I was setting up the spin waves in a way, and I was also creating supercells so that the spin waves fit in contrast, for example, to EMTO. But what you see here, so KKR means effectively a very simple KKR LMTO SA method, so something that we actually developed. Then we compared it to EMTO, to a full charge density EMTO. And then I also tried the same thing with LSMS to see how this works. And this reproduces actually the magnetic moments, and the energy is quite accurate. Okay, here is some discrepancy, but the difference between the magnetic moments can, yeah, I think this is still something that's okay. And here you can see actually it reproduces the energy within a range of a few millirad compared actually to the, I guess, more accurate full charge density EMTO. So this is actually everything of my new results that I want to present now at this point. So now let me conclude. So maybe let's point out the most important things. So I showed you a transferable methodology to correct this systematic error in DFT. Then I showed you an efficient ab initio based method for predicting the solid solution strengthening in random alloys, which really helps finding non-equimolar alloys with favorable mechanical properties. And the workflow is part of an Adaman software toolkit, which is a toolkit for setting up these locations and in general for Green's function-based modeling of mechanical properties. It also includes dissipation optimization for material parameters, for example. Then I want to acknowledge my funding agencies and also want to make some, I want to advertise the Green's function method that we are developing here in Leoben, or there in Leoben actually. It's called GreenArm, which stands for Green's function-based alloy modeling. So the main developers are Oleg Pyle, Professor Andrei Rubin, and Gabo Shire, and yours truly. So thank you for attention, and yeah, I'm open for questions.